Welcome to the fundamental lecture in electronics. This is for the first year EEE program. The main contents that we are going to cover in the electronics fundamentals are the semiconductor basics, then we will move to PN junction diode, and the third we will cover the bipolar junction transistor fundamentals. So in this video lecture, we will focus on the semiconductor in detail. So semiconductors, first let us understand the semiconductor materials. So what are semiconductor? Semiconductors are a special class of elements that is having conductivity between that of a good conductor and that of an insulator. So we can classify the material as, first category we can say that there is a conductor whose conductivity is very good. Second, we have insulator which is having the bad conductivity, or the material is fully insulating in nature. Hence, the semiconductor are those materials whose conductivity lies between the conductor and the insulator. Semiconductor materials generally fall into one of the two classes. First, there is a single crystal structure. For example, the germanium and silicon, which is having a repetitive crystal structure. The second one is the compound material. Here the example are gallium arsenide, cadmium sulfide, gallium nitride, gallium arsenide phosphide. And they are constructed from two or more semiconductor materials that are having different atomic structure. So different atomic structure are combined to form the compound, and in silicon crystal we have a crystal structured solid material made up of only one element, that is either germanium or silicon. The three semiconductors that are frequently used in electronic devices are germanium, silicon, and gallium arsenide. These are the most frequently utilized electronic devices semiconductor material. If we talk about the conductors, for example, silver, copper, gold, and they have one valence electron. Valence electron means the number of electrons at the last orbit or the final orbit of the atomic structure. So when we talk about the conductors will have only one valence electron, but when we talk about the insulator, they will have 8 valence electron. Now hence, since semiconductors fall between the conductors and the insulators, it will have 4 valence electron. So conductors will have 1, insulators will have 8, and semiconductors will have 4 valence electrons. Many years ago, it was only the germanium which was considered to be the suitable material for the semiconductor devices. But germanium devices had a fatal flaw, which we will discuss, that is the reverse saturation current, which is very high. Then engineers need to overcome this. We know that next to oxygen, silicon is the most abundant element on the earth. The advantage of silicon immediately made it the semiconductor of choice because it is mostly available. Now, silicon is generally used in the electronics, communications, and computers, and without which the semiconductor, the electronic devices are not possible. Now, here we have an isolated silicon atom which is having 14 protons and 14 electrons. So we can see the atomic structure of the isolated silicon atom. Here we have the 14 protons and all the electrons are present at the different orbits. When we talk about the core net charge, which is 14 because it contains 14 protons in the nucleus and 10 electrons are there in the first two orbits. So core is made up of the nucleus and the first two orbits, which is having 14. So we can say that here we have the core to be the net charge of +4, and these are the valence electrons which are present in the outermost orbit of an atomic structure of silicon. So we have total 4 electrons which are present in the outermost orbit, which are the valence electrons. Now let us see the energy band. The range of energies which is possessed by electrons on the same orbit in a solid is known as energy band. So we have seen that the electrons will be revolving in an orbit, and each orbit will have its own energy which are known as energy band. Now when we talk about a single isolated atom, electrons revolving in any orbit possess a definite energy. However, when we talk about a complete solid, an atom is greatly influenced by the closely packed neighboring atoms. So, when we have the isolated atom, it is only the energy which is there in the particular cell. But when we talk about the solid, the atoms which are present in the neighboring will also have an influence. Because of the neighboring atoms, the electron in the same orbit have a range of energies rather than a single energy. So we don't have a single energy concept in case of atom, because the other atoms which are present in the neighbor will have an influence. Although there are a number of energy bands in the solid, but we are more concerned with the following. So if we draw the energy band of insulator, semiconductor and metals, we will be having the two different bands. One is known as the valence band and another is known as the conduction band. The distance between the valence band and the conduction band will decide whether the material is insulator or it is semiconductor or it is a metal. So we can see that when the conductor is there, then there is no gap between the valence band and the conduction band. This gap for the insulator is quite large, whereas for semiconductor the gap is small. And we have certain electrons which are present in the conduction band. No electrons are present in the conduction band of the insulator. So, three most important terms which are associated with the energy band is the valence band. Valence band is the outermost orbit electron in an atom and it is the highest energy level. When we talk about the conduction band, loose electrons responsible for the current conduction. So the electrons from the valence band will move to the conduction band and they will be responsible for the conduction of the current. Hence, it is the conduction band. The forbidden energy gap is the gap between the valence and the conduction band. So whatever the gap is there between the valence band and the conduction band, this is known as forbidden energy gap. If we see the silicon crystal atomic structure, we will find that the silicon atoms arrange themselves in an orderly pattern which is known as the crystal. So when we see that all the atoms in the silicon crystal are arranged in an orderly fashion, and this is to be a solid which is known as the crystal structure of the silicon. Each silicon atom will share its electron with 4 neighboring atoms. So this is the first silicon atom and it is shared with the other silicon atoms which are present in the neighboring. So total 4 atoms are present in the neighboring of one silicon atom. This sharing allows each atom to have a total of 8 electrons in its valence orbit. So if we see that how many electrons are present in the valence orbit, you will find that this is 8. And hence the covalent bond will be formed between the atoms due to the equal and opposite force of attraction. So these are the covalent bonds which are formed between the atoms. Billions of such covalent bonds hold the silicon crystal together, giving it the solid structure. So crystal will be having the solid structure because of the covalent bond which is formed between the different atoms. Now each atom in a silicon crystal which is having 8 electrons in the valence orbit, these configuration results in the chemical stability and give a solid material. The tendency to combine and share electrons to achieve high 8 electrons in the outer orbit, the reason for which 8 electrons provide stability is not fully understood, but it is observed in various materials. So why we have 8 electrons which gives a better chemical stability and the material is solid, that is not fully understandable. Now some scientific laws such as the law of gravity or the Coulomb's law, they are also not fully understood. And similar to this, even the advanced physics equations are partially explain the stability of 8 electrons in the different materials. But it has been observed that when the 8 electrons are present, it is saturated because no more electrons can fit into the orbit and hence the chemical structure will be better. We know that the surrounding air temperature is known as the ambient temperature, and at temperature above absolute zero, which is minus 273 degrees centigrade, the heat energy cause the atom in a silicon crystal to vibrate. So the atoms will vibrate when the temperature will increase. So higher ambient temperature result in stronger mechanical vibrations. And when we feel the warmth, when picking up a warm object is due to the vibrating atoms. So the atoms present in the crystal will vibrate, and which result in the warmth felt in the warm object. Now in semiconductor we will be having the free electrons and the holes, which will be responsible for the conductivity of the semiconductor. So the vibrations in the silicon crystal can dislodge the electrons from the valence orbit. So these vibrations are produced because of the heat, and the electrons which are present in the valence orbit will be dislodged. The released electrons gain through enough energy to move in the larger orbit become a free electron. So electrons will move from one orbit to another orbit of higher energy. The departure of the electron creates a vacancy in the valence orbit, which is called a hole. So when the electrons move from one orbit to the another, then there the hole is created. So this is the hole, and here the electron has moved. Holes behave like positive charge and can attract and capture nearby electrons also. So it is the holes which are treated to be positive charge, because electrons are the negative charge and holes will have a positive charge. Holes are formed only when the electrons move from one orbit to another higher energy. The presence of holes is a critical difference between the conductor and the semiconductor. So when we compare the conductors and the semiconductor, the holes create a major difference. Now what is the role of doping and what is doping? Doping is basically the impurities which are added to the semiconductor. We will discuss this in more detail ahead. So in the room temperature, thermal energy will produce only a few holes and the few free electrons. So the conducting particles, whether it is a holes or electrons at room temperature, will be very less, and this has to be because of the thermal energy. If we need to increase the number of holes and the free electrons, the crystal need to be doped. So we need to be doped or put impurities in the semiconductor so that the number of conducting particles, whether it is holes and free electron, increases. Now, what is recombination and lifetime? When we talk about a pure silicon crystal, the thermal energy generated an equal number of free electrons and holes. So if the semiconductor is pure, the electrons and holes will be in equal number, and these free electrons move randomly throughout the crystal. So occasionally a free electron and a hole come close to each other and there is a recombination. So electrons which are negative charge particle and holes which are positive charge particle, there is a recombination because of them coming nearby to each other. The recombination is the merging of a free electron and a hole, and the time between the creation and disappearance of the free electron is called the lifetime. So when the electron is formed and when the electron and holes are combined, the time gap between that is known as the lifetime of an electron. The lifetime can vary from few nanoseconds to several microseconds depending on the crystal quality and other factors. So this lifetime is very short in nanoseconds and microsecond time. So the main points that we can note in the silicon crystal, point number 1 is creation of free electrons and holes which are generated due to the thermal energy. Second point is recombination of free electrons and holes, because when they recombine, then the charges disappeared and no more free electrons are there for conductivity. The third point is temporary existence of free electrons and holes. So electrons and holes exist temporarily waiting for the recombinations. So these are the main 3 points which we have discussed on the silicon crystal. So here in the figure we can see that a particular silicon atom is surrounded by 4 silicon atoms. And when the thermal energy is there, then the electron will move from its orbit and move to the higher energy. And hence there will be a formation of hole. And when this recombination of electron and holes are there, then we have the charges to be disappeared. So the lifetime of the electron occurs from its occurring to its recombination. Now we will discuss what is intrinsic semiconductor. An extremely pure semiconductor is called intrinsic semiconductor. So when the semiconductor is extremely pure, it is known as intrinsic semiconductor. At absolute zero temperature, that is minus 273 Kelvin, the valence band of an intrinsic semiconductor is completely filled and the conduction band is completely empty. So we do not have any free particles for conduction. But when we put or give the heat energy, thermal energy, some valence electron will be lifted to the conduction band, creating free moving electrons and holes. So now, due to the heat energy, conducting particles, that is the electrons and holes, will be there. Intrinsic semiconductor have negative temperature coefficient. What is the meaning of negative temperature coefficient? That its resistivity will decrease and the conductivity will increase with the rise in temperature. So if you increase the temperature, the resistivity will fall and the conductivity will increase. This is known as negative temperature coefficient. When we talk about the extrinsic semiconductor, the extrinsic semiconductor are used because the intrinsic semiconductor on its own is not at all useful for the electronic devices. To make it conductive, a small amount of suitable impurity is added, resulting in an extrinsic semiconductor. So extrinsic semiconductor are the impure semiconductor which are added with impurities. The process of adding this impurity to a semiconductor is known as doping. So when we add the impurities to the semiconductor, that process is known as doping, and it needs to be closely controlled because the doping process has to be done very minutely. Extrinsic semiconductors are classified based on the type of impurity added. So again, this extrinsic semiconductor will be divided into two different types. One is N-type semiconductor and another is P-type semiconductor. So N-type semiconductor are formed when a donor impurity atom is added, creating excess free electrons. So more electrons will be there. That is known as N-type semiconductor. P-type semiconductor, when an acceptor impurity is added, which is resulting in more holes creation. That is known as P-type semiconductor. Again, N-type semiconductor, because electrons are there, it is negatively charged particle. P-type semiconductor, because more holes are there, they are positively charged. Now we can see here how the hole will flow through a semiconductor. So these free electrons, which will be moving from one of the orbit to the another, or the energy state, when the potential will be applied or the electric field will be applied, then the electrons and holes will be formed. When we talk about the intrinsic semiconductor, the number of electrons and the number of holes are equal. So intrinsic semiconductor do not conduct and hence not useful for electronics. If we have the doping, that is, if we add more electrons or more holes, then only the conducting particles may be there in the silicon crystal or the semiconductor, and the semiconductor will be known as extrinsic semiconductor, which will be used for electronics. Let us see the N-type semiconductor. So when a small amount of pentavalent impurity, pentavalent means it will have 5 valence electrons, is added to a pure semiconductor, it creates an extrinsic semiconductor known as N-type semiconductor. So N-type semiconductor are formed due to the donor impurities, and donor are basically pentavalent. Pentavalent means 5 valence electron. So pentavalent impurities, example arsenic and antimony, which provides a large number of free electrons in the semiconductor crystal. These impurities are called donor impurities because each atom donates 1 free electron to the semiconductor crystal. So one impurity atom will donate 1 free electrons in the semiconductor crystal. Hence, more number of donors has to be there. The pentavalent impurity atoms fit into the crystal structure with their 4 valence electron forming covalent bond and the 5th electron being free. So when we talk about the 5 valence electron in pentavalent atom, the 4 valence electron will form the covalent bond and the 5th electron will be free for the electric conduction. The small amount of pentavalent impurity results in a large number of free electrons available for conduction. Hence, these pentavalent impurity will increase the conduction. Next, we'll see the P-type semiconductor. So if the impurity added is trivalent, that is having 3 valence electron in the pure semiconductor, then the extrinsic semiconductor form is known as p-type semiconductor. So trivalent impurity atoms, if we take the example like boron, gallium, indium, it produce free holes in the semiconductor crystal. Now, why these holes are formed? Because since these impurity atoms are the acceptor impurities which are having 3 valence electron, so one hole will be formed with one atom. The reason is here you have the 3 valence electron and we require 4 electrons to form the covalent bond. So it means you have -1 electron, which is known as the holes, and which result in the conduction. So again, if we have the trivalent impurity, the conduction will increase in the semiconductor. So the summary of this extrinsic semiconductor is, if we have n-type semiconductor to be formed, pentavalent impurity atoms has to be added, more electrons will be formed, and they are known as donor impurities. If we have to form p-type semiconductor, then trivalent impurity atom has to be added, and free holes will be formed, and they are known as the acceptor impurities. So here we see the n-type and p-type semiconductor. N-type semiconductor will have more electrons as compared to holes, and in p-type semiconductor more holes will be there as compared to electrons, whereas the electrons and holes will be equal in case of intrinsic semiconductor. What is mass action law? So when we have the thermal equilibrium, the product of the number of holes and electron is constant and independent on the amount of donor and acceptor impurity doping. So this is under thermal equilibrium. So we can say that number of electrons and number of holes product is equal to Ni square, where Ni is the intrinsic concentration under thermal equilibrium, and N and P are the free electrons and holes in per unit volume of the crystal. While considering the conductivity of the doped semiconductor, only the dominant majority charge carriers have to be considered. So if we are considering the extrinsic semiconductor on doped semiconductor, which is the majority doping that we need to consider? So let us understand the charge densities in the doped semiconductor. So if we have the n-type semiconductor, then in n-type the number of electrons will be equal to the donor impurity electrons plus the hole, and the majority charge carrier will be the donor electrons. From mass action law, we can know that the number of holes will be equal to Ni square by Nn. So in n-type semiconductor, it is basically the majority is the donor impurity atoms. So we can say the number of electrons will be equal to number of donor impurity atoms, and number of holes will be equal to intrinsic concentration square divided by Nd. So these are the number of electrons and holes present in the n-type semiconductor. Whereas in the p-type semiconductor, the number of holes will be majority equal to the acceptor impurity atoms. And from the mass action law, we can say that the holes will be equal to Ni square by the holes which are having Ni square by the acceptor impurity atoms. So the number of holes will be equal to number of acceptor impurity atoms, and number of electrons will be equal to Ni square, that is the intrinsic concentration, divided by the acceptor impurity atoms. So these are the charge densities in n-type and p-type semiconductors. Let us understand the extrinsic conductivity, the charge particles. So if we have the n-type semiconductor, the conductivity will be given by Q, that is the net charge on the electron, number of electrons into mobility. So that is normally equal to Q into Nd into mu n, because the number of electrons present will be equal to the number of donor impurity atoms. Whereas in the p-type semiconductor, this formula will remain the same, only in place of n-type we have p-type. So here the number of holes present will be equal to the number of acceptor impurity atoms. In case of p-type semiconductor, the donor atoms has to be added exceed the acceptor impurity atoms. If Nd is greater than, very greater than Na, then p-type can be converted to n-type. Similarly, you can convert the n type to p type if Na is very greater than Nd. So one of the semiconductor n type can be converted to p type, or p type can be converted to n type, depending upon the condition whether the donor is more than acceptor or acceptor impurity atoms is more than donor impurity atoms. Let us solve one problem to understand the phenomena of semiconductor conductivity for a silicon material. So the intrinsic condition at a room temperature of 300 Kelvin, we have to find what is the intrinsic conductivity. What if the donor impurity we have to find in 1 into 10 to the power 8, which is given. The acceptor impurity 1 in 5 into 10 to the power 7, and with both impurities present simultaneously. So these are the different points that we need to find. How many intrinsic conductivity material electrons and the holes are there? If we are added with a donor impurity, what will happen? If we add with the acceptor impurity, what will happen? And if both the impurities are equally present, then what will happen? Now here, some informations are given that the intrinsic concentration for silicon at 300 Kelvin is 1.5 into 10 to the power 10 centimeter minus 3. The mobility of electrons and holes are also given 1300 and 500 centimeters square volt second. And the total number of silicon atom in the volume, that is per centimeter cube, is 5 into 10 to the power 22. So we have to determine the concentration. Let us see the solution. In intrinsic condition, we know that number of electrons and number of holes will be equal, which will be equal to Ni, and the charge will be equal to Q into Ni, and the total mobility will add mu1 plus mu2. So we can find it is 4.32 into 10 to the power minus 6 Siemens per centimeter as per the data given. Now, if the impurity added is basically the donor, then what is the number of donor impurity atom added that we need to determine when the number of silicon atoms are 5 into 10 to the power 22. We also know that the majority carriers are the donor will be the electrons. Hence, from the mass action law, we can find the number of holes is equal to Ni square by Nd, which is equal to 0.46 into 10 to the power 6. And hence, the conductivity we can determine using the formula of number of electrons into charge into its mobility. Here, Nd value we have already computed as 5 into 10 to the power 14. And charge on the electron we know 1.6 into 10 to the power minus 19. Mobility given 1300 for electron. So we'll get the conductivity as 0.104 Siemens per centimeter. On the other hand, if the acceptor impurity atoms are added, then we need to find how many acceptor impurity atoms are there in 5 into 10 to the power 22 silicon crystal, which is equal to 10 to the power 15, because it is 1:5 into 10 to the power 7. And the number of holes, that is the majority carriers, are equal to the number of acceptor impurity atoms, and from the mass action law, the number of electrons is equal to Ni square by Na, which is equal to 2.25 into 10 to the power 5. And hence, the conductivity formula will have the number of acceptor impurity atoms multiplied with the charge on the electron multiplied with the mobility of the holes, which gives 0.08 Siemens per centimeter. Now, if both the impurities are present, then we have to decide which impurity is more, whether it is acceptor or whether it is donor. We have seen here in the problem, the acceptor impurity atom is more than the donor impurity atoms. Hence, overall, the semiconductor can be treated as p-type semiconductor with the number of acceptor impurity atoms is 5 into 10 to the power 14. Hence, the conductivity formula we will put Na dash down, that is the excess of the p-type semiconductor, and here we will put the mobility of the holes, because this semiconductor is basically the p-type semiconductor. So we'll get 0.04 Siemens per centimeter. Now we will see the semiconductor currents due to the drift current and the diffusion current. So flow of charge current through a semiconductor or PN junction diode has two components. So when we talk about the current in the semiconductor, it is because of the two components. One is the drift current and second is the diffusion current. Now, what is the difference between the drift current and the diffusion current? Let us see. So when we talk about the drift current, it arises from the movement of carriers in response to an applied electric field. Electric field means the potential which we are applying, and hence the carriers will move. So positive carriers, which are the hole, will move in the same direction as that of the electric field. But if we have the negative carriers, the electrons will move in the opposite direction. And the net motion of the charged particle generates a drift current that is in the same direction as that of the applied electric field. So here we can see from a pictorial representation that when electric field is applied in this direction, then the electrons will move in the opposite direction and hole will move in the same direction of the electric field, and the total current will be in the same direction of the electric field. So drift current density J in unit ampere per centimeter square is given by, overall the formula can be remembered as J is equal to Q into charge particle, whether it is electron or the holes, into movability multiplied by the electric field. We have seen that this formula is basically the conductivity, and we know that J is equal to sigma into E. So sigma is the conductivity which we have found in the previous discussion. Now for the free electrons, we will be having N into mu N, and for the holes we will have P into mu P. And hence we can find the drift current density for the electrons and the holes. When we talk about the diffusion current, the current can flow even in the absence of applied voltage, provided a concentration gradient exists. So we don't have the voltage which is applied, but concentration gradient is there between the particles. So when the number of either electrons or holes is greater in one region as compared to the other region, then concentration gradient is formed, and from the higher concentration to the lower concentration, the charge particle will move. And hence, there will be a movement of charge carrier which is known as diffusion current, and this is because of the concentration gradient. So here we can see that the movement of the holes and the electrons in the p-type and n-type semiconductor, even in the absence of voltage, but only the concentration gradient. So the diffusion current density J is given by, for the hole it is the concentration gradient dP by dS multiplied with dP, that is the diffusion constant, and Jn indicates the diffusion current density for electrons, that is dN by dx into dN, that is a coefficient constant. So hole density Px decreases with increasing x, hence negative sign is already incorporated here. So Jp is positive in the positive x direction. So when the concentration gradient in the positive x direction, the J value is positive, and these dN by dx and dP by dx are the concentration gradient, whereas the diffusion coefficient unit centimeter square by second are given by dN and dP constants. So if we talk about the total current, it will be the summation of the drift current plus the diffusion current. So whatever the formula we have derived, that is the drift current plus the diffusion current, and this negative sign is coming from here, we'll get the total current density for the holes and the electron. It will be the summation of the drift and the diffusion formula that we have derived. Now Einstein has given one relationship between the mobility and the diffusion coefficient for a particular type of charge carrier in the same conductor. So dP by mu P, that is the diffusion coefficient by the mobility of the holes for a semiconductor, is equal to dN by mu N is equal to kT by Q is equal to Vt. Now K here is the Boltzmann constant, T is the temperature, and Q is the charge on the particle. So Vt is the thermal constant. Higher the charge carrier mobility, so if the mobility is more, greater will be the tendency to diffuse. So diffusion current Jp or Jn for the diffusion will be more. And this Einstein relationship is used to determine the diffusion constant dP by dP and dN by experimentally measuring the mobility of the holes and the electrons. Let us see one problem. If we have a p-type semiconductor, the length is being 5 cm, cross-sectional area 1 cm square, and a doping concentration of 1 into 10 to the power 16, which is subjected to an electric field of 100 volt per meter, calculate the drift current in the semiconductor. So the given data, let us note down the length of the semiconductor, cross-sectional area, the doping concentration NP, and the electric field. These are the data which is given to us. Hence, we can find the drift current density, which is Q into E, and Q is given by the charge, mobility, and the number of electrons product. We'll get 2.24 into 10 to the power minus 3. And once we have determined this current density multiplied with area, we'll get what is the total current due to the drift current. So this is 2.24 into 10 to the power minus 7 ampere. You can see that the current is very less. It will be in micro ampere. Next problem. Here we have a silicon bar with a length of 2 mm, cross-sectional area 0.2 mm square. Excess minority carrier concentration is 3 into 10 to the power 14 centimeter minus 3. The diffusion coefficient for the minority carriers in silicon is given. Calculate the diffusion current. So in the previous problem, we have calculated the drift current. Now we calculate the diffusion current. So first we note down what are the data is given, the length, cross-sectional area, the concentration of the electrons, and the diffusion coefficient. And first we need to find the dN by dx, because that will be substituted in the diffusion current density formula, dN by dx. So dN by dx is nothing but the charge carrier n by the total length, which is equal to 1.5 into 10 to the power 78. And hence the diffusion current density we can find out from the first formula, putting the value of dN by dx. So that will give me a current density, and hence the current, actual current due to the diffusion will be the current density multiplied with the area of the cross section. We'll get 4.8 into 10 to the power minus 18. So these complete the basic discussion on semiconductors. In the next topic, we are going to take PN junction diode, and then we will take the bipolar junction transistor, which will complete the electronics fundamentals of the first year EEE program. Thank you for now.